In this section, we're going to talk about arc length, and specifically kind of how we can extend ideas about arc length that we would have learned within Calc 2 to this new context of vector functions in Calc 3. So back in Calc 2, you might actually remember this formula here for the arc length for a parametric curve. You might also recall that it's extremely similar to an arc length formula that we had for non-parametric functions. So like early on in Calc 2, you would have established an arc length function that would have looked like this. But when you got to parametric functions, you see that it's almost a similar in shape formula we establish here with a derivative of x with respect to t, derivative of y with respect to t. So the nice thing is that this formula actually extends into the world of 3 dimensions very, very nicely, specifically because the distance formula actually extends very, very nicely into 3 dimensions, as we saw back in Chapter 1. So before we're able to kind of jump to the theorem that talks about the arc length, we first need to identify or kind of define some important terminology here. So if we take a look at the definition here, it states that a parameterization R of t will be referred to as smooth on a specific interval, or it could be considered smooth everywhere, if it is the case that the derivative of r is continuous, meaning again that each of its component functions are continuous. And it also has to be the case that r prime of t never is equal to the 0 vector. Remember right there, that's a bolded 0, so that's a 0 vector for any t. So we saw back in some of the previous sections that once we calculated r prime, we could evaluate it at various points in time. We could create kind of tangent vectors on our vector function at various points. But as long as it's the case that that never turns into the 0 vector at any time, and as long as all those component functions are continuous, we call this vector function smooth. So we'll say an entire curve is smooth if it has a smooth parameterization. And kind of intuitively, if you're thinking about a curve in 3 space, if I have a curve that like does something like this and is moving around, like this here would be considered a smooth curve. Okay? Everything here is really nice. At any given point in time, I could identify a tangent vector. Components are going to be continuous. I'm never going to get a tangent vector probably of 0. But if I have something that has like a sharp corner in it, or maybe like a cusp, then maybe something like this is not going to end up being smooth, specifically because of like this problem point that I have right here. Okay, so now that we understand a little bit about what it means for a parameterization to be smooth, and we know how to check for that, we can introduce the following theorem. So the theorem here says, suppose that we have a vector function r of t, and we're imagining this is here in 3 space, so it's got 3 component functions. And as long as this is a smooth vector valued function, and as long as it's the case that the curve is only traversed one time as we go from A to B, then this would be a formula for the arc length of the curve. You'll notice that's again extremely similar to what we had back in Calc 2. It is just going to be adding on this extra dz dt term also being squared underneath our radical. The other thing here, though, that's kind of cool is that if I look at kind of what I have here, these different pieces actually represent the derivatives of all of my component functions. And so the derivative is then having each of its components being squared added together under a radical. You'll note that over here I just say, well, couldn't I just think about that as the norm, the magnitude of the r prime vector function? And so this is an alternative way that we could write it. Okay. Now, so again, some really important things here to highlight is that there are really 2 conditions here that I need to check. First, I need to make sure that I have a smooth vector valued function. If I don't have a smooth vector valued function, there's no guarantee that this formula here actually works. The other thing is I have to make sure that the curve is traversed exactly one time. Meaning that I got to be really, really careful that I don't have a curve that, say, goes and does something like this, to then just kind of stop at a point and retrace backwards the other way. So I can't do any like retracing over the curve. I have to traverse it exactly one time. Okay? As long as those conditions are met, then this formula here should be able to tell me the length of the curve. And the next video we'll take a look at kind of a partial proof for how we could actually verify that this is indeed going to be the arc length formula.